Hey everyone, and welcome. Have you ever wondered if there's a secret code hidden inside of change itself? I mean, something that stays the same even when everything else is being twisted and stretched? Well, there is. And today, we're going to dive into this really cool concept from math that, believe it or not, powers everything from your Google searches to how engineers build safer bridges. So yeah, let's pull back the curtain and see what's going on. So here's the game plan. First, we're going to look at the simple idea of an unchanging direction. Then, we'll see what happens when that direction gets stretched. After that, it's time to meet the eigens. You'll see what that means. Then we'll figure out the secret they're hiding. And finally, wrap it all up with why this is so important in the real world. It's going to be a fun ride from a simple picture to a huge idea. All right, so let's just start with this big, kind of philosophical question. When you change something, I mean really change it, you stretch it, you twist it, you transform it, is there anything at its core that stays the same? Anything that holds steady through all of that? It's a cool question, right? And to answer that, we're going to start with something super simple, a visual. I promise no crazy equations here. We're just going to look at a picture and see what we can figure out. Okay, so first up, I want you to imagine a simple grid, like a piece of graph paper. It's just a bunch of points all lined up perfectly. And we can draw these little arrows or vectors from the very center out to any of those points. Simple enough, right? All right, now for the fun part. Let's mess with it. We're going to apply something called a transformation. Basically, we're going to warp this grid. Imagine grabbing the corners of that graph paper and just stretching it. Or maybe shearing it, kind of pushing the top to one side. The whole thing gets distorted, but in a really neat, predictable way. So, look what happens when we do that. If you pick some random arrow, some random vector, and track it, bam, it gets totally knocked off its original line. Its direction is completely different now, and its length probably changed too. This happens to pretty much every single vector you could pick. Almost. That almost is the key. So what about the ones that don't get knocked off course? In all of this stretching and warping, are there any special vectors that just hold their ground? Let's go find them. And here they are. This is so cool. See? Amidst all that chaos, a few special vectors do something amazing. They don't change direction at all. The transformation happens and they just stay on their original line. Sure, they might get stretched out or squished or maybe even flipped completely backwards, but their path, that straight line they're on, is totally unchanged. They're like the calm center of the storm. Okay, so this whole property, this idea of a direction that doesn't change, is a huge deal in math. So of course, it has a special name. Let's give what we've just seen a proper introduction. These special guys are called eigenvectors. It's a German word, and eigen basically means own or characteristic. And that's the perfect way to think about it. An eigenvector is like the transformation's own special direction. It's the characteristic, the fundamental axis of that change. And what about the stretch? How much longer or shorter did it get? Well, that has a name too. It's called the eigenvalue. It's just a number, a simple scaling factor. So if the eigenvalue is, say, 2, it means the eigenvector got twice as long. If it's 0.5, it got cut in half. Pretty straightforward, right? The eigenvector is the direction, and the eigenvalue is the stretch factor. So what's the big takeaway here? It's that these two things together, the eigenvector and the eigenvalue, are like the secret key to understanding the transformation. They literally reveal its DNA. They show you what the change is really doing at its deepest level. And this is the process right here. It's like a recipe. You start with any system. Could be an image, a bridge, a whole social network. Then you apply some kind of change to it. A force, a link, whatever. The next step is the magic one. You find the special directions that don't change, the eigenvectors. Then you just measure how much they stretched, the eigenvalues. And boom, you've just uncovered the fundamental skeleton of that entire transformation. It's that powerful. Okay, so this is all really neat math, but so what? Why does this actually matter? Well, get ready for this, because it turns out this one single idea is the engine running under the hood of some of the most incredible technology we rely on every single day. I mean, the list is just mind-blowing. Google's PageRank, the algorithm that built an empire, that was all about finding the eigenvector of the entire internet to figure out which pages were most important. Worried about bridges collapsing? Engineers use this to find the exact vibrations, the eigenfrequencies that could be dangerous. Facial recognition software? It uses eigenvectors to find the eigenfaces, the core features of a human face. It's in data compression, it's deep in quantum mechanics. This idea is, and I am not exaggerating, everywhere. So, at the end of the day, what these eigen things really show us is that even inside the most complicated, messy changes, there are these beautiful, simple, stable rules hiding underneath. And that just kind of makes you wonder, doesn't it? What other invisible rules are out there just hiding in plain sight, shaping our world in ways we haven't even noticed yet?